This is our technical presentation for Group 15's Park and Spin Highway project. The overview of our task was the product had to fulfill the requirement specified, which is to span the 6 lanes of highway, including a 10-foot median, must be set up in less than 30 minutes for highway shutdown, be set up with very little prep work, and be fully transportable on all Oklahoma roads and highway systems, excluding cities. There had to be signage included with cameras, sensors, and withstand environmental factors such as ice, wind, and other environmental factors. Our design approach consisted of understanding the regulations that we were provided with from the Oklahoma Highway Institute, the Department of Transportation, and OSHA, followed by the needs of the company that asked us to do this. So we started with understanding the regulations for what we needed to do and incorporated our requirements into it. We selected our material based upon what would fit our loading analysis and stresses correctly, and then we based our designs on how easy the setup would be to limit any traffic interference. And we repeated this process until we came to our final design. Transportation regulations. We based our design around how best to transport it. Regulations and design effects. Regulations were the biggest driver of the design and how we implemented our brainstorming. More notably, the transportation of our system was highly constrained by what would be allowed on roadways without permits, without any special permits, and would actually be able to be set up in a decent amount of time without closing the highways for more than 30 minutes. Setup regulations. What sets Park and Spin up apart from its competitors is its incredibly fast setup time. We literally designed it so you could just park on the side of the road and spin it out and set up an additional vertical stabilizer to make sure it would be able to withstand the loads that we put onto it and the environment put onto it. Attachment regulations. Park and Spins comes with all required attachments. A small screen, light, sensors, and cameras over each lane, and then a large 15 by 5 foot screen facing the direction of traffic. Handrails for OSHA certification are also a part of the design to make workers safer.
Design overview. The following design elements were agreed upon for the final design. A single trailer could deploy and span up 3 lanes in a small median. For 6 lanes of coverage, a second trailer is necessary. The trailer would have a hydraulic jack to elevate the structure spanning over the road. The structure would rotate out perpendicular to the trailer to deploy. The structure would telescope out to the desired span of coverage. Material selection. Since the maximum weight allowed was 75,000 pounds, lighter materials were not a priority. The material chosen needed to be strong and somewhat flexible. The main span material was chosen to be AISI 4140 steel because of its high strength and good strain capacity before yielding. As the steel is relatively cheap material that is extremely workable into different shapes. Design sketches. The compacted design is shown on the left. In order to deploy to minimum configuration shown on the right, the highway is first shut down and the arm is swung across to the nearest median. Then the secondary support structure will be extended down. At this point, both support structures will be raised in tandem to the operational height of 15 feet above ground. Design sketches continue. When encountering more than a three-way highway, we recommend a second Park and Spin for full lane coverage. The cross-highway beam can be extended telescopically up to 3 lanes, which is why a second is needed for 6 lanes. Because of varying median length, we found it most economical to use 2 separate Park and Spins. 3D and SolidWorks model. Here we have a very rough SolidWorks model to kind of get an idea of how this would actually look in 3 dimensions. Design analysis. All analysis done at maximum length/loading to ensure the system would work in all regimes. This includes the ice loading. Critical load points were identified to be reactionary forces at either end of the structure. Modeled all signs, cameras, and sensors as point loads, while modeling the weight of the arm as a distributed load. It was determined that the trailer needed only to pass the load down to the jacks released by the trailer. It was assumed that the beam should be modeled as a single width beam. Design analysis. So here we have a free body diagram and a shear diagram and a moment diagram. Design analysis. To ensure that the beam would be able to handle the loads of the signs, sensors, cameras, etc., we designed it to be a square beam with a hollow square cut out, leaving a 2-inch thick wall for the beam. The team started by performing the von Mises yield criterion to get a number that we would design around. The maximum yield strength, accounting for a factor of safety of 1.5, came to 40.13 psi. The sizing for the supports, this is at both ends, were designed from the maximum yield strength. Design analysis. We referenced this chart when picking our factor of safety. We concluded that we were using reliable material where loading and environmental conditions are not severe. We chose a factor of safety of 1.5 because we felt it provided the best balance between weight and safety. Our team came to the conclusion that this factor of safety was also acceptable in accounting for fatigue. Design weight statistics. And here we have a breakdown of the weight of the different components of the beam. Design dimensional statistics. And here we have a breakdown of all of the diameters and the heights of all of the different components of the beams and the supports. Do note that all the dimensions are for outer surfaces. For cross-highway beam thickness is 2.1. The support structure thickness is 0.125, and this is excluding the top half inch of upper member, which is a solid steel plate. Design analysis, and this is for ice loading.
Ice loading was one of the major environmental factors that changed how our design would sit statically on the roadway. The ice actually added a significant amount of weight, which changed our shear and moments of our structure and added some additional strain on key connecting points. We took these new loads into account and made sure we designed our structure to be as safe as possible. Design analysis, wind loading. Our wind loading applies only to the horizontal direction, is how we interpreted what the wind load was, especially from the provided source materials. Given that our structure ended up being higher than 16 feet, we took it upon ourselves to assume worst case scenario and did all our calculations for the next highest value, set for the 40 meters per second value, which is 90 miles per hour of wind, which is easily able to withstand most of the windy days here in Oklahoma. Given the forces that this wind applies to our structure, we decided to incorporate torsional dampeners into our design to allow for a more resilient structure, not collapse or be otherwise burdened by the additional forces. Key components.
Some key components of our design are the cross-highway beam, the main support structure attached to the truck, the secondary support structure, the trailer and truck, and the motors and controls needed for setup. Requirement Achievement Assessment. Despite a high weight, this is an effective system. The product can deploy quickly and safely. It can withstand all weather conditions easily due to generous factors of safety within the design. Overall, this would be a desirable product for state transportation department to purchase. Our designs took all given requirements into full consideration to be able to fit everything into the structure and be compact as possible, to be as compact as possible. The regulations from local and national government were also given priority in design, and we are confident in the compliance with these rules. Conclusion, recommendations, and potential issues. After analyzing the design, we have come to the conclusion that this is not only a viable design, but a realistic one as well. Some changes that could be made in changing the hollow crossbeam to a truss-like structure that would not only reduce weight, but cost as well. Our reasons for not doing this in the first place was that we do not know how to analyze a truss member. For a more complete structural analysis, it would be best to have more detailed knowledge of hydraulics and the ability to carry load. So we kind of left the hydraulic part out of most of our analysis. References, and these are the references we used when designing our structure.